Explanation: a SR set reset flip-flop is the simplest memory cell. Its symbol looks like a small box with two inputs labeled S set and R reset on the left and two outputs Q and Q bar, the complement of Q on the right. Internally, it can be built with two cross-coupled NAND gates or NOR gates. Gate implementation NAND version. The output of the first NAND is Q, its inputs are S, and the output of the second NAND Q bar. The output of the second NAND is Q bar, its inputs are R and Q. This feedback creates a bistable circuit. Once Q goes to 1, it stays there until R forces it low and vice versa. Truth table for NAND-based SR, where a low input means active. S0 R1 Q next 1 set, Q becomes 1. S1 R0 Q next 0 reset, Q becomes 0. S1 R1 Q next Q no change, memory holds. S0 R0 Q next undefined, illegal. Both outputs try to be 1 race condition. In a NOR-based version, the active level is high, but the table is the same after swapping 0 and 1. The symbol, gates, and table together give a clear picture of how the SR element stores 1 bit of information. The characteristic equation describes how the next state Q plus depends on the present inputs and present state. For an SR latch built with NAND gates, active low inputs, the equation is Q plus equals not open S and not Q close equals S prime plus R and Q, where the prime, pronounced as not, denotes logical not. Another common form uses the Boolean sum of products. Q plus equals S plus not R and Q. The excitation table is used when we design a circuit that must move from a known present state to a desired next state. It tells us which input combination S, R will cause that transition. For each pair Q, Q plus, the table lists the required S and R. Present Q0 next Q plus 0, S1, R1 no change. Present Q0 next Q plus 1, S0, R1 set. Present Q1 next Q plus 0, S1, R0 reset. Present Q1 next Q plus 1, S1, R1 no change. Notice the illegal transition 0 to 1 when both S and R are 0, active low, which would force both Q and Q bar to 1, a forbidden state. The excitation table is a handy lookup when converting a state transition diagram into actual SR latch connections. A timing diagram for an SR latch shows the relationship between the two inputs S and R and the output Q over time. Imagine a train station where a signal S tells the train to depart Q equals 1 and another signal R tells it to stop Q equals 0. The train Q remembers its last command until a new command arrives. Setup time T setup is the minimum time that S or R must be stable before the controlling clock edge or before the latch becomes transparent. Hold time T hold is the minimum time the inputs must stay stable after that edge. If these windows are violated, the latch might capture a transient value leading to uncertainty. Race through or race condition occurs when S and R change at the same instant while the latch is transparent. Because the two NAND gates feed each other, a tiny propagation delay can cause the circuit to race through multiple states before finally settling, sometimes landing in the illegal 0-0 or 1-1 condition. In practice, designers add a small delay element or use a master-slave arrangement edge-triggered flip-flop to eliminate this race through ensuring the latch only reacts to inputs at a well-defined instant. A typical timing diagram marks the clock or enable high period when the latch is open. S and R pulses placed well within the setup hold windows. The resulting Q waveform that changes only after the clock edge, demonstrating the memory effect. Explanation: AD, meaning data flip-flop, is derived from the SR latch by forcing the two inputs to be complementary, so the forbidden state can never occur. Think of it as a one-way hallway where you can only go forward, set, or stay where you are, but you can never step into the hallway from both ends at the same time. Derivation: connect the S input of an SR latch to the data input D, and connect the R input to the complement of D bar. This guarantees that S and R are never both low active simultaneously. Symbol: a small box with a single input D, a clock or enable input C, and two outputs Q and Q bar. Often a small triangle on the clock line indicates edge-triggered behavior. NAND gate 1 receives D and the clock, through a gating network. NAND Gate 2 receives D bar and the same clock. The outputs of these NANDs feed the cross-coupled NOR/NAND pair that stores Q. Truth table level sensitive active high clock. Columns are C clock D Q+. When C is 0, D is any value, Q remains unchanged. When C is 1 and D is 0, Q+ is 0. When C is 1 and D is 1, Q+ is 1. When the clock is low, the flip-flop simply remembers its previous state. When the clock goes high, Q follows D by adding a master-slave arrangement. We make the device react only on a rising or falling edge, turning it into the ubiquitous edge-triggered D flip-flop used in synchronous designs. The characteristic equation of a D flip-flop expresses the next state directly in terms of the data input D. Q+ equals D. Because the D input is the only variable that can change the state, the equation is trivial. The flip-flop just copies D at the triggering instant. The excitation table therefore only needs to indicate that to get a desired next state Q+, you simply set D equal to Q+, regardless of the present state. Present Q0 next Q0 D0. Present Q0 next Q1 D1. Present Q1 next Q0 D0. Present Q1 next Q1 D1. The edge-triggered behavior is achieved by cascading two-level sensitive latches master and slave clocked on opposite phases. The master is transparent when the clock is low, the slave when the clock is high. The overall effect is that the output Q changes only on the clock transition, for example, rising edge. Think of a relay that closes for a split second at the exact moment a traffic light turns green. The car's data may be moving, but only the cars that arrived exactly at the green moment are allowed to pass. Q of T+ equals D of T edge, where T+ is the time immediately after the clock edge. This clean, deterministic mapping makes D flip-flops the backbone of synchronous digital systems. Timing parameters tell us how fast a flip-flop can reliably operate. Setup time T sub setup, minimum interval that D must be stable before the clock edge. If D changes too close to the edge, the internal latch may see a partially changed value. Hold time T sub hold, minimum interval that D must remain stable after the clock edge. This ensures the data captured by the internal master latch does not drift. Clock to Q delay T sub CQ, time taken for the output Q to reflect the new value after the clock edge. It is often split into clock to Q minimum and clock to Q maximum to account for process variations. Propagation delay T sub PD, general term for the time a change at any input, including clock, takes to affect the output. For a DFF, the dominant propagation path is clock to Q. Edge analysis. For a positive edge-triggered device, the safe clock period T must satisfy T greater than or equal to T sub setup plus T sub CQ max plus T sub skew plus T sub margin, where T sub skew accounts for differences between launch and capture clock edges, and T sub margin is a design safety margin. Practical analogy. Imagine a photographer, the clock, taking a picture of a moving object. The data D, the object must be in the right position, stable, a little before the shutter clicks, set up, and must stay still a moment after, hold so the picture isn't blurry. The time it takes for the camera to develop the image is the clock to Q delay. If the photographer clicks too fast, period too short, the picture will be out of focus, similar to timing violations in digital circuits. The SR flip-flop and D flip-flop both store 1 bit, but they differ in how the inputs are interpreted. Inputs 2 independent signals S set and R reset, versus a single data input D plus clock. Prohibited state, S equals R equals 0, active low, or S equals R equals 1, active high, both outputs forced 1 undefined. For D flip-flop, no illegal combination, D is simply copied. The complementary input D bar guarantees safe operation. Typical use, simple control where you need explicit set and reset commands, for example start-stop latch, asynchronous clear, versus synchronous data storage, shift registers, counters, state registers, anywhere you need a reliable edge-triggered memory element. Edge-triggered version requires extra gating master-slave to avoid race-through, otherwise level-sensitive latch, versus naturally realized as master-slave, edge-triggered behavior is inherent. Real-world analogy, 2 separate levers, one pushes the door open, set, the other pulls it closed, reset. Pulling both simultaneously jams the mechanism, versus a single switch that either passes the current signal through on a clock tick or holds the previous value. No chance of a jam because there is only one control line. Because the D flip-flop eliminates the illegal state, it is far more common in modern synchronous designs. Whereas SR latches still appear in asynchronous reset circuits, memory-enable lines, and teaching examples to illustrate feedback and bistability. Explanation: designing a synchronous sequential circuit follows a systematic flow, whether you pick SR or D flip-flops. 1. State table: list every possible state of the machine and the required next state for each combination of inputs. Example for a simple 2-bit up counter. Present Q1 Q0 input X, next Q1 plus Q0 plus 00 input 0 next 01. 01 input 0 next 10. 10 input 0 next 11. 11 input 0 next 00. 2. State diagram: convert the table into a directed graph where circles are states and arrows show transitions, annotated with input conditions. This visual helps spot unused states or hazards. 3. Flip-flop assignment: choose the flip-flop type. SR implementation: use the excitation table to translate each required transition Q leads to Q plus into S and R values for each flip-flop. Then derive the Boolean expressions for S and R using Carnot maps. D implementation: simpler. The excitation table tells you D equals Q plus directly. So for each bit, the D input equation is just the next state function for that bit. 4. Logic minimization: simplify the resulting Boolean equation sum of products or product of sums to obtain the minimal combinational network feeding the flip-flops. 5. Verification: simulate the timing diagram, checking setup hold times and ensuring no illegal SR condition appears. If you used SR and generated a forbidden 1-1 condition for any input combination, you must add a reset or redesign. Example: using the 2-bit up counter above with DFFs. The next state equations are D sub Q0 equals not Q0. D sub Q1 equals Q0 exclusive or Q1. These are implemented with an XOR gate and an inverter, feeding 2 D flip-flops clocked by the same clock. The design is fast, glitch-free, and free of illegal states. When SR flip-flops are required, for example asynchronous reset, the same flow applies, but you must also handle the extra SR logic and verify that the race-through condition is eliminated, typically by adding a master-slave edge-triggered stage. State transition table completion: you are given a partial table and asked to fill missing next state entries. Use the excitation table. For SR, write S and R for each Q to Q plus pair. For D, simply set D equals Q plus. Verify that no illegal SR combination appears. Frequency division: design a divide by 2 counter using a JK or D flip-flop. Strategy: connect Q bar to the D input or toggle JK inputs and feed the same clock. The output toggles each clock edge, giving a frequency half of the clock. Metastability assessment: a problem may ask whether a given asynchronous input could cause metastability in a D flip-flop. Strategy: check if the data changes within the setup hold window of the clock edge. If it does, the flip-flop may enter a metastable region. The solution is to add synchronizer stages, cascade 2 D flip-flops to allow the uncertain voltage to resolve before it propagates further. Timing violation calculation: provide clock period, T setup, T hold, TCQ, and ask whether a design meets timing. Compute the required clock period using Tmin equals T setup plus TCQ max plus T skew. If the given clock period is less, the answer is no, a violation occurs. Race through elimination: given a level-sensitive SR latch, the exam may ask to modify it to avoid race through. Strategy: insert a master-slave arrangement or add a small delay RC or gate so that during the transparent phase, only one of the inputs can change at a time. Conversion between flip-flop types: convert an SR implementation to a D implementation. Show the algebra D equals S plus not R times Q, or simply replace S with D and R with not D. Demonstrate the resulting truth table. General tip: always start by writing down the fundamental equations, characteristic excitation, and the timing constraints. From there, draw a quick timing diagram to visualize setup hold windows. This systematic approach prevents missing hidden conditions such as illegal SR states or metastable windows.